You ever stare at a really complex math problem and just wish there was some kind of secret shortcut? Well, for a certain type of differential equation, there actually is. So let's dive into this amazing trick that turns what looks like terrifying calculus into some pretty simple algebra.
Okay, first, let's set the stage here. We're talking about a very specific type of problem, higher-order linear differential equations with constant coefficients. Now, that sounds super complicated, I know, but trust me, it's not. Higher order just means it's got second derivatives or even higher. Linear means no squared terms on your y's, and constant coefficients, well, that just means the numbers out front are fixed. These things are everywhere, modeling real-world stuff like electrical circuits and vibrations.
So, take a look at this. You've got the double primes, the single primes. Yeah, it can look pretty intimidating. And if your first thought is to just, panic a little bit, hey, that's totally normal. But what if I told you there's a really elegant way to crack this thing wide open?
That's the big secret right there. We are going to perform a little bit of mathematical magic. We're going to transform this calculus beast into a simple algebra problem that, honestly, you probably solved 100 times before. You ready?
This entire shortcut, the whole beautiful trick, it all hinges on making one very, very clever assumption about what the solution is supposed to look like. And here it is. We're just going to assume that the solution, y, is an exponential function, e to the power of r times x. Now, why this specific form? Well, look back at the original equation. It's a bunch of derivatives all added up to equal 0. And what's the one function we know that basically keeps its own shape when you differentiate it? The exponential. Its derivatives are just multiples of itself. And that property, that's the key.
And this is where the magic really happens. Just look what happens when we take the derivatives. The first derivative, y prime, it just brings down an r in front. The second derivative, y double prime, brings down another r, giving us r squared. The calculus part is literally turning into simple multiplication.
So what's the next logical step? We take these new expressions for y, y prime, and y double prime, and we're going to plug them right back into that scary equation we started with.
After we substitute everything in, and then factor out that e to the rx term that's in everything, this is what we're left with. Now you know the rule, right? If you have two things multiplied together that equal 0, one of them must be 0. And here is the key that unlocks the entire puzzle. That e to the power of rx term, it can get incredibly, incredibly small, but it can never, ever actually equal 0. It's impossible. So what does that mean for us? It means we can just divide both sides by it, and poof, it's gone. We can just ignore it.
And just like that, we've done it. The differential equation has completely vanished, and in its place is this simple quadratic equation. This right here is called the characteristic equation. No more derivatives, no more calculus, just a polynomial we can solve easily.
Okay, so now we are on very familiar ground. We have a simple algebra problem, so let's go find its roots and use them to build our final answer.
All right, basic factoring. We need two numbers that multiply to positive 6 and add up to negative 5. Let's think. Gotta be negative 2 and negative 3, right? So we can just factor our equation into r minus 2 times r minus 3 equals 0. Easy enough. So since r minus 2 times r minus 3 equals 0, that means either the first part is 0 or the second part is 0. If r minus 2 is 0, then r has to be 2. If r minus 3 is 0, r has to be 3. And there we go. We've got our two roots. r1 is 2 and r2 is 3. These two numbers are the core of our final solution.
Now, this is important. Anytime you solve one of these and get two different real number roots like we did, there is a standard template for the answer. It's a combination of those exponential forms we assumed at the start, with c1 and c2 being just some constants.
So all we have to do is plug our roots, 2 and 3, right into that general form. And there it is. That's the solution to that crazy-looking differential equation from the beginning. Pretty incredible, isn't it? Okay, so what we just did was the perfect ideal case. But what happens when the characteristic equation gives you something a little weirder? Let's level up.
I mean, what if you factor your equation and you get the same root twice? Or what if the roots aren't even real numbers at all, but they're complex numbers that involve I? Does the whole method just fall apart? Nope. Don't worry, there's a plan for that too.
You just have to use a slightly different template for the solution. It's all about following the pattern. If you get a repeated root, see how you just multiply that second term by x? That's it. And if you get complex roots, it's a little wild, but thanks to a beautiful thing called Euler's formula, they create solutions with sines and cosines. You just have to pick the right formula for the job.
So we have covered a lot of ground here.
Let's boil this whole powerful process down into a simple, actionable checklist that you can use every single time.
Here's your game plan. Step 1. Convert the differential equation by replacing the derivatives with powers of r. Step 2. Solve that new equation for its roots. Step 3. Use those roots to build out the general solution with e to the rx. Step 4. Stop and check. Do you need one of the special case formulas for repeated or complex roots? And finally, Step 5. The most important step to make sure you're right.
How do you actually know for sure that you didn't make one tiny little mistake along the way? There is one final, crucial step that really separates the amateurs from the pros.
You have to always check your work. Take that solution you just found, find its derivatives, and plug them all the way back into the very first equation. If the left side cancels out and equals 0, you've absolutely nailed it. This step builds so much confidence and guarantees you have the right answer.
You know, this whole method is just a perfect example of how a clever change in perspective can make a really difficult problem just fall apart. It kind of makes you wonder, doesn't it? What other complex challenges are out there just waiting for the right shortcut to be discovered?